Hi everyone. First of all, I would like to give a big shout out to all the organizers of Conf42. Thanks a lot for this smooth conduct. It has been a very fantastic experience for me. Amazing job, guys. Hi. Thanks for joining me in this talk. I'll be talking about experimentation platform at scale. I'm Riteek Srivastava. I work as a lead software engineer at Gojek in data engineering team, currently in a stream called experimentation. In this talk, I'll be walking you through my experience of building A/B testing platform at Gojek, the challenges which we faced, right, and the changes in architecture which we did to cater the new throughput, the new scale, which is right now is around 2.1 or 2.2 million RPM. Let's proceed. Yeah, so this is the title of my talk, A/B testing platform at scale. Let's move to the next slide. Yeah, so the agenda of this talk will be like I'll be explaining about what A/B testing is, and then we will talk about the objective, what the audience of this talk can learn from this. Then I'll be explaining about the litmus, the name of A/B testing platform at Gojek. Then give a light on the old architecture from where we started building the platform. Then we will talk about the current scale or the scale, how the number of experiments, number of clients, the adoption experimentation has increased in Gojek. And then we will talk about the new architecture, how we have made changes in the new architecture to cater the new scale. So what is A/B testing? A/B testing is basically a randomized experimentation process wherein two or more versions of a features are shown to different segment of users at the same time. After running the experiment for some days or weeks, we analyze the data, and then this data helps us determine which version leaves the maximum impact and drive the business metrics. Let's for an example understand this concept with an example. The allocation algorithm, right? The allocation algorithm is is used for allocating drivers to customers. Suppose you have a existing algorithm which is allocating drivers to customers. Now you have a hypothesis that by changing few of the parameters in your allocation algorithm, you will be able to uh, allocate your driver efficiently to your customers, which will impact your business metric, which is booking conversion metric, and this metric will increase by making this change in the algorithm. So what you will do, instead of directly rolling this out algorithm to production, which can be very uh, critical and dangerous because you do not know whether how this will perform in production, right? So you will be running an experiment with the existing algorithm and the new algorithm which you are proposing. You will run this experiment for a few weeks and collect the data, and then you will analyze the data and see for which variation the booking conversion rate has increased. If it is a new variation, then you will be rolling that out to all the users in a staggered manner. If it is not, then you are sure that whatever you thought was not right, and the current algorithm is performing better than the suggestion, the new algorithm, right? So let's move to the next slide. Yeah, so these days a lot of companies are investing in experimentation. Not only big giants, even small startups are also doing experimentation on daily basis. So whatever apps which you are using right now these days, right, it must be running at least few hundreds of experiments on each app, because this makes sense as well, right? Because it is the data which is leading you to make the decision, right? Not just that your manager or some high paying people are coming and saying that this is how we should do it and this will perform better and we are rolling this out to all the users. This decision is backed by data, right? So I'll quote one of the quote by Jeff Bezos. Like, what he said is that if you double the number of experiments per year, you are going to double your inventiveness, right? He also knew that how critical experimentation is for a particular firm. So Amazon also must be running a pretty huge number of experiments for its uh, different services, right? So let's move to the next slide. Yeah, litmus. What is litmus? So Litmus is basically the name of experimentation platform at Gojek. This actually has two core features. One is A/B testing, which we call experiment, where you come and define your experiment with two or more variants, and you can do the A/B testing. Second one is a staggered rollout, right? Once you have the result of your experiment, you can uh, promote your winning variant to a release, like rolling that out to all the users in a staggered way. So that is called release. Uh, these are the two features currently supported by Litmus. The third one is that it also supports the targeting rules. I am uh, purposefully mentioning this here because if you see here, right, we have a kind of rules like app version newer than 1.2, 3.12, sorry. So all the users who will have the app version newer than this will be part of this experiment. So these are some rules which we support. So I'm mentioning this because for each experiments we need to pass the rules for the experiments, right? Which makes this application as a CPU intensive. I want to highlight this word because it will be used in the system design. Also, it will help us design the system better because we know the expectation from this application, right? So yeah, so these are the key features supported by Litmus, which is the A/B testing platform of Gojek. So what is the objective of this talk, right? So I'll be walking you through my experience of building the Litmus from scratch to uh, uh, also the changes which we made to the system to cater the high throughput. So what are the non-functional requirements which we will need to build this system? So these are the core non-functional requirements. First is the low latency. Low latency is required because if you see, right, experimentation is a new call in your flow, right? Suppose if you are running an algorithm for driver allocation, right now you have only one algorithm, so you know which algorithm to use. If you are running an experiment, you added one more branching there, right? You will talk to the experimentation service, get to know which algorithm to use, and then you will use that algorithm. So this low latency is very critical here because it is going to impact the overall flow, right? Second one is the highly available, which I think is given for all the systems. The system has to be highly available because it is being used in a lot of flows. A high throughput in the sense because in Gojek, pretty much every services are using this platform for running experiments. So we are expected to get the high throughput. Weak consistency, basically the data should be eventually consistent. Like if anyone making some changes in the experiments, it should eventually be reflected on the client side. Yeah, these are the objectives. Let's go to the architecture, how we started. So let's look into the initial architecture, how the idea of Litmus is started, how we built the uh, version 1 of Litmus. So we have this Litmus server, right? So Litmus server is basically a A/B testing platform, the application which have all the functional requirements like supporting experiments, releases, rules, etc., which is backed by Postgres. We have a primary database Postgres, right? So how the initial flow was? We had a portal actually. So the experimenters can come to portal, can create experiments, update their created experiments. Basically, can do any kind of CRUD on their experiments. So how the flow was? Whenever they are making any changes on the portal will talk to the Litmus server, and Litmus server will reflect that changes to the DB. And we have clients are basically the, you can say, microservices or mobile clients, any clients which needs to talk to experimentation platform to decide which variants to use, right, which variation of an experiment to use. So how does this flow work? Clients talks to the Litmus server, and Litmus server talks to the DB, fetches all the valid experiments and return those to clients. So this is the initial architecture. Uh, you must be thinking that this is pretty naive and there are a couple of limitations here. Yeah, and we will be talking about those limitations in the next slide. Let's go to next slide. Yeah. So limitations. First one is the single cluster handling the request of read and write. Right. So what is the problem here? So the problem is the read throughput and write throughput are very different for Litmus. The read throughput is around 6 to 7x larger than the write throughput, right? So the tuning, the scaling required for the read will be different from the write, right? So if we are using a single cluster and suppose uh, read is using a lot of resources, right? It might affect the write, right? Suppose if there is some outage happened on that cluster, read and write both will be affected by those. So this is one of the uh, potential problem in this whole architecture. The second one is primary database being used for read and write. So we have a primary and uh, uh, recovery database. Primary is basically which will handle all the writes and read both. Other replicas are basically where you can read the data. If we had the read clients directly read from the application server through directly read through replica database via Litmus application, it will be better in the performance that even if the primary database is down, they can read through the replica database, which is like reading the data is a critical flow here, right? Because a lot of the microservices will be talking to the experimentation platform at API level, right? So even if the primary database is not performing well or running some kind of maintenance, they can read from the recovery database, right? The third one is a single deployment. Single deployment, as in, like if you are making any changes related to write APIs, the deployment will go for both the read and write, right? If you are making any changes related to uh, read APIs, like any optimization you have done, you will have to make the deployment, and that deployment will affect both read and write, right? So the separation for read and write is not here, which we will talk about in the next slide. So what we did next, we separated the read and write cluster, right, to scale it better because the throughput difference was quite large. So let's go to the architecture. We have a Litmus write servers, we have a Litmus read servers, we have primary database, and we have replica, which will be replicating all the data on its from primary on its side. So how the portal will be talking right now? So portal will talk to the write servers, and similar to the previous fashion, the write server will make those changes in the DB, and all the clients now will be talking to read servers, and read servers will be talking fetching the data from replica and returning them to clients. This is how the system will look like once we segregate the read and write clusters. Let's go to the pros and cons of this architecture. Pros. Read and write cluster can scale independently, which is correct, right? If your read throughput is increasing insanely, you can just scale your read cluster, and even if your read cluster is for some time affecting the response time, right? Because of the high throughput, your write cluster or your portal will not face any kind of issue until and unless the issue is on the database side, right? Decoupled deployment, the deployments will be faster, right? Because the read changes and the write changes are independent now, right? The deployment on read is not affecting the write, and vice versa, because anytime on a high throughput service, if you are doing a deployment on day, right, so it will affect all the clients that time. So if we have a read and write client separately, we will not we will be able to deploy the write cluster at any time because it is a low throughput service. Third one is the master slave setup, basically primary or a replica setup, here the write cluster is talking to the primary database, and the read cluster is talking to the replica database. So you can tune the replica database to increase the number of connections for your applications, right? And there won't be much load on the master, right, because it will only be serving the write write throughput. So there are some cons as well, which I think we will understand later in the talk. The cons are all the clients are sharing the resources, right? Means there are a lot of clients which are talking to experimentation platform. They all have a common resource, like the read cluster has some amount of CPU, right? That CPU is being shared by all the clients requests, right? It is a problem. I'll explain this in the later section. Not horizontally scalable is the second con, or the limitation, I would say. It is because the underlying database is a Postgres, right? You can have certain amount of connections there, right? If you're going to do the horizontal scaling, each server will be making a connection to database, right? So you need to keep in mind that as well. It's not easily horizontal scalable. Whenever you are reaching the max connection configured on the DB side, your server will be crashing, right? Because it will not be able to get the ideal connections with the DB. So this is one of the limitations in the read write segregation cluster. Yeah, so let's talk about scale over time, which is important to understand the changes in the architecture needs to be done to uh, support the new scale, right? So let's see how the number of clients, number of experiments, or the number of releases has changed over the course of time. Let's see the number of clients over time. So from 2019 to 2022, I would say, see the number of clients, how it has increased, right? Every quarter it is increasing, right? Somewhere it is increasing slow, and somewhere it has increased by a big margin, but the trend is increasing, right? It is not any time at constant trend. So this is one of the major part in the scale, that the different clients will be talking to your systems now, right? And each client can have different requirements. Some clients can run 100 of experiments, some will be running 2 or 3 experiments, right? So there is a diversity in the clients as well. We'll talk about that later. Let's see the number of active experiment at a time over a course of period. From 2019 to 2022, right? If you see, we started with 178, we reached to 739, and now in 2020 end we were about 1.8k. These are the active experiments, like running experiments. We have excluded the completed or stopped experiments. So this actually is the distribution of clients experiments, the number of experiments running for a particular client. You see, it's pretty uneven, right? So the expectation from the clients is also very different, right? Few clients will be running 100 of experiments. They are okay with the large response time. Few clients are running only 2 and 3 experiments, but they are not okay with the large latencies, right? Because the response time is proportional to the number of experiments, right? Because we have the rule configured for the experiments, and we have to parse a rule for each experiment, right? So somehow this response time is proportional to the number of experiment running for a client, right? So here, if you see, it is not only the overall scale, it is also the diversity in the client, right? what is the expectation from each client. If we are sharing the resources, right? Suppose some clients is okay with like large latency, suppose 50 ms as 99 percentile, but some clients are not okay with it, right? Because they're only running one or two experiments. Why would they want their 99 percentile to be this high, right? So this was one of the other concern. Let's look the similar graph for releases. This is the trend for the active releases over course of time, and this is the distribution of number of releases per client. This is similar to what we saw in the experiment, and the problem is also the similar, right? And if you see the numbers are also similar. We had around 1.8k experiments at the end of 2022, but in releases we had 1.6k. And now you see in 20 from 2022 to 2023 we have already contributed, like increased the active releases by 2k. So you are looking, you see the scale, right? How is it increasing? So let's see what changes we made in the architecture to cater this release, right? Cater this scale, sorry. So let's look at some of the points here. That every year Litmus is receiving a new scale, right? At the end of 2019, the max throughput was coming around 100k RPM. These all numbers are RPM. I forgot to mention in the slide. At the end of 2020, it was around 500k RPM. At the end of 2021, it was around 1.1 million RPM. At the end of 2022, it reached to 2 million RPM. So, so the last two architectures we saw, right? The very basic and naive architecture with a single server, and the second one with a segregated read and write cluster, were able to handle around 500k throughput within the committed SLA. Beyond that, it was like the responses were frustrated, and we were seeing some errors as well because of the resource scarcity, right? So looking at the adoption and the growth of experimentation per year, right, which we saw in the scale slide, right, how the number of experiments and releases are increasing over a course of time. We adopted a sidecar pattern to optimize the latency, right? Why sidecar pattern? Sidecar pattern because by doing sidecar, if you are running the sidecars on the client server, you are distributing the resources, right? So resources are distributed. So if some clients want to run 1,000 experiments, right? Say 1,000 is a random number. Say 100 experiments want to run, right? So they will be configuring that much of resources to the sidecar, right? If some clients are running only one or two experiments, why would they bother to give good resources? They will just be giving one code to that sidecar, right? Or less for running the sidecar. So this came to our mind because of the diversity in the clients, right? We thought that let's make it distributed. Let's make the resources distributed and build the platform so that it can handle the scale as well as the diversity in the scale. Let's look at the architecture diagram now. How does it look like? We have a write servers, right? We have the primary database. So portal flow will be similar to what it was, right? The portal will all the portal requests will go to the write server, and write server will be reflecting those changes in the primary database, right? Now how the clients will be connecting? So these yellow boxes are client servers, and these are the client processes in gray, right? So we have deployed the sidecar processes along with the client main process, right? These sidecars will be syncing the data from write servers periodically. Let's say 5 seconds every 5, which is a configurable value. Every, let's say, t seconds, they will fetch all the experiments for that particular client, and they will store it in Badger TV. Sidecar uses Badger TV. So periodically they are syncing the data from write server, and write server has a API exposed, which is basically fetch all the data and will return it to sidecar processes. So they will every t second they will be fetching the data from write server and store that in the Badger DB. So whenever a client make a request to sidecar will read the data from the Badger DB and do all the rule parsing and everything and return the valid experiments to client. So if you see this, right, here all the computations are distributed over each servers, right? Rather than doing all the computations on a particular set of servers, it has been distributed. So by this architecture, it can scale to uh, any value, right? Because here we are not making any direct connection with the database. We are syncing the data via API, right? The connections are maintained by the write server with the database, right? And also the API, the client's response time of the response time of one of the client is not getting affected by others, right? Let's see the key points for the sidecar pattern. So given sidecar is distributed, it is designed with the availability and consistency. So using this PACELC theorem, basically if we have a partition, we will have to choose between availability and consistency, else we have to choose between latency and consistency. So sidecar has been built with uh, choosing the availability over consistency in case of network partition and consistency over latency uh, if there is no network partition, right? So uh, we decided to go ahead with this. We had a survey with our clients and we decided to go ahead with this. We do not have right now the options to configure the sidecar to support both uh, consistency and latency with a configurable value. Right now, sidecar just support availability in case of network partition, else consistency. Second one is horizontally scalable, which I already talked about, right? Since it is not making direct connection to the database, right? It is horizontally scalable. Like you can literally spin up like hundreds of thousands of servers which will talk to the Litmus servers periodically, right? Because the throughput on the sidecar is not directly proportional to the throughput on the write application. Because if you see here, the call between sidecar process and write servers is happening periodically every t seconds. So irrespective of this throughput, right, the client process to sidecar process, this throughput is not getting affected. So it is horizontally scalable. So the third part is resources are distributed, which I already explained, right? The response time of a client will not be affected by the experiments of other clients because the resources are distributed and their clients will be running the sidecar on their own resources. And also we have a central monitoring for all the sidecar on the New Relic and Grafana, because as a experimentation platform, if we are providing a sidecar, we need to check the health of all the sidecars as well, right? If someone is complaining that my sidecar is not working, you need to have the observability, right? What is the issue? Is it working fine? Since when it is not working? So we have monitoring as well for all those sidecars. Yeah, so this brings us to the last section of the uh, talk, basically how the throughput and response times look like right now. This is one of the screenshot I have took while making this slide uh, at a particular time. So if you see, this is reaching up to 1.61 million RPM, the throughput. And if you see the 99 percentile, right, it is pretty efficient, 9.52 ms, right? You see the scale and the response time. This is the like most optimized thing which we were targeting for, and using this sidecar pattern we were able to deliver this, right? And make the system uh, more available and more diversified according to to support the uh, requirement of different clients. So yeah, this is the overall learning for me while building the experimentation platform. Yes, so currently we are focusing mostly on the building analytic systems, but I think that is not the part of this talk, that is out of scope of this talk. So yeah, that's all from my side. Thanks a lot. Please reach out to me on Twitter or LinkedIn for any questions you have. I have written a few blogs as well on this. If you are interested, you can go on Medium. And thanks a lot. Have a nice day, guys.